All right, so let's look at another one of these examples that's actually going to be a proof that's going to rely on a few different cases. So in this case, we're going to be looking at this statement that claims if you give me any random integer, so in this case, I'm going to refer to this thing as an a, if I have the property that a is not going to be congruent to 0 mod 5, then two different things can actually occur. On one hand, I'm going to say that if you square this thing, it's going to kick out a 1 in the mod 5 world, and on the other side of the coin, it's going to say that a squared could potentially be negative 1 mod 5. So in this case, there's actually a couple different ways you can go about this thing, but the easiest way is actually just going to attack this thing directly and just think about all of the different cases that this could actually introduce. So in this situation, what's going to happen is that I know right now that a cannot be 0 mod 5. So the question is, what could a potentially be in this mod 5 setting? Well, I know if I'm looking at things in this mod 5 world, what's going to happen is that I'm basically going to cycle through all of these different little remainders, and essentially they're all going to kick out either a 0, a 1, a 2, a 3, or a 4. So in this situation, after I hit 4, I'm going to start repeating these things. So the idea is that if I kicked out a 5, I know that 5 is going to be congruent to 0 in this mod 5 world, so it doesn't really make sense to have to kind of double dip on that side of things. In this case, this mod 5 world is actually chunked up into 5 little bins. So in this case, I'm just throwing away one of those bins and I'm going to test the other 4. So in this situation, if I look at, let's say, if a happens to be 1 in this mod 5 setting, well, what's going to happen if I take this 1 and square it, what I'm going to end up getting is an a squared, which is going to be a 1 squared, and I know that 1 squared just turns into a 1, so it's going to stay a 1 in this mod 5 world. So in this case, it's actually being lumped into that first potential outcome. So let's see what happens next. If I take, let's say, a to be 2 in the mod 5 setting, well, what's going to happen is if I square this thing, it's going to change just a little bit. I'm going to get a 2 squared, which is going to initially kick out a 4. And I'm going to think about that and be like, well, you didn't say anything about a 4. I see a 1 and a negative 1. Well, in this case, if you think about negative 1 and positive 4 are actually congruent to each other in this mod 5 setting. If you think about it, if you take that 4 and just subtract a 5 from it, it's going to bring you down to negative 1. Or you can think about this as the idea that 4 is actually equal to 5 minus 1. So in this case, if I do the modulo 5 stuff, that's going to disappear, and you have that these things are going to be congruent mod 5. So in this case, I do end up kicking out that negative 1, which is good. There is a little bit of reason on why I'd want to introduce this negative 1, and we're actually going to allude to this just a little bit at the end of this video. The idea is that this result actually becomes a super important result in the world of this RSA encryption, and what I can do is I can replace that 5 with any prime number I want to, and if I change those powers just a little bit, they're going to indicate these 1s and negative 1s as well. So rather than having to think about this negative 1 as actually 1 less than that prime, I'm just going to view this as this negative 1. So that's this case. That's kind of why I'm using this weird negative 1 notation, but if you think about it, it's just going to be subtracting the 5 off of it, or whatever prime you're starting with. Okay, so next up on this pathway, we're going to have 3. So 3 mod 5, if I square both sides, I'm going to end up with a 3 squared, which I know is a 9, and here's where I'm going to have another one of these negative 1s. In this case, I could take that 9, I can subtract off 5 twice, and I'm down to negative 1, so I'm going to have negative 1 mod 5. And last but not least, I'm going to take a to be 4 mod 5. And if I square this thing, I'm going to get a 4 squared, which is 16, and that's going to kick me down to the positive 1 worlds. In this case, it's going to be a positive 1. So in all 4 cases, you can see that I've tested all 4 of these versions. You can see that I either kick out a positive 1 or I kick out a negative 1. And that's exactly what this result is saying. The idea is that as long as you're avoiding 0, you're going to have either a 1 or a negative 1. Obviously, we know for that we start with 0, and if I square it, it's just going to kick me into the 0 world, so that's the one that I'm wanting to avoid. So in terms of trying to write this thing up just a little bit, I'm basically going to sketch out exactly what we just got done doing, but just putting a little bit of verbiage in front of this thing. So the idea is that if you start with any integers such that a is not 0 mod 5, I know that it's going to be in one of these 4 cases. So I'm going to test these cases 1, 2, 3, and 4, kind of in this case separately. And then I just do that exact computation that I just got done doing. Case 1 is the case that I'm going to be a is congruent to 1, square it, you see it kicks out a 1. The 2, you square it, it kicks out a negative 1. The 3, you square it, it kicks out a negative 1. The 4, you square it, it kicks out a 1, and you're done. And that's all it is. So it's kind of just taking this kind of scratch work that we do over on this page and just cleaning it up just a little bit. All right, so I actually alluded to this just a little bit when you're first kind of exploring this example and testing a bunch of things, is that we can actually take this example and generalize it just a little bit. And what I mean by generalize is that I can take this very nice little statement that has a lot of really cool things going on, and I can make it just a little bit better. And the way that I can actually make this particular statement better is by changing up the prime number that I'm working in. So in this situation, I chose 5 because it's a really nice little small prime number, and I knew that when I dove into the world of cases, I was only going to have to do 4 cases, and that's about as many as it looks like I can fit on the screen, so everything works great. But the idea is that when you have a statement that looks something like this, what you want to think at the back of your head is that, can I change things up just a little bit? Or does this only work with 5? Or could it potentially work with 7 or 11 or any prime number you'd ever want to? So this idea of being able to take a statement and change it to something that involves just general primes is going to be something that's going to be super important as we move into Units 4 and Units 5. In particular, this idea of being able to have something that's true for every prime is going to become super, super important in this world of encryption and decryption. The moment that I can start doing things to any randomly chosen prime number is going to be super powerful. So this particular example actually is one of those things. I can actually change that 5 into any prime I'd ever want to, but I have to change the little power that comes with it as well. It's not going to be good enough just to have these little squares. Those powers are actually going to be dependent upon whatever random prime I started with. And that's actually the reason why I chose these -1s and 1s, because I wanted to see those things always remaining the exact same as long as I changed the prime and the power. So in this situation, what's going to happen is that if you change your prime 5 to any other prime, that power is actually going to change into a p minus 1, all of that divided by 2. And you can see that that's actually going to work for 5, because you can take the 5, you subtract a 1 off of it, it's going to kick out a 4, and then if you divide that thing, it's going to kick out a 2. So if you want to, you can test a few of these examples. So in this case, I have Sage code down below that's actually kind of showing us why this may or may not be true in this situation. So the first example is going to be all 4 of those cases that I started with. So it's going to be this little for loop that's going to cycle from 1 up to that prime number -1, which in this case is 4. So it's going to print out the numbers, so 1, 2, 3, and 4. It's going to print out the square. And then ultimately it's going to print out that square, and then it's going to be reduced modulo 5. So in this case, we can see the 1s and the 4s popping out, which were exactly those examples that we saw back in this world. I have the 1, I have the 4, I have the -1, and I have the 1. I know the -1 and the 4 are actually the same, but in Sage it's just going to kick out the 1s and 4s. So in that case, it does provide a nice check to see exactly what's going on. If I try to jump this thing up to another prime, so in this case if I test 7, well, if I try to compute p minus 1 divided by 2, that's going to kick out a 3. So if I cycle through this loop from 1 up to 6 now in this case, because I'm going to in this case have 6 different cases, I'm going to compute all those powers, and then they're going to be raised to the power of 3, and then ultimately trying to reduce this thing modulo 7. And you can see in this case I'm going to be kicking out a whole bunch of 1s and 6s, and I know that 6s are going to be -1 in this world, so it appears to check out. Next up, you can test it with 11. So in this case, you're going to take 11 minus 1, which is going to be 10. 10 divided by 2 is going to kick out a 5. So you're going to run kind of these cases from 1 up to 10 in this situation, because you're going to have 11 possible little remainders. I'm going to throw away the 0, 1, and then do the rest of them. So 1, 2, 3, 4, all the way up to 10. In this case, if you take all those numbers, raise them to the 5th power, and reduce them modulo 11, you again see a whole bunch of 1s and 10s emerging. So it does appear that this result has this potential to become cooler. We don't at this stage have the techniques to actually show why it's true. We're going to need one super duper awesome result, which is referred to as Fermat's Little Theorem, and that's going to come up in this section on induction, which is actually the next big topic of this course. Once we have this notion of induction and Fermat's Little Theorem, we can actually revisit this result to show why this thing is going to be true in general. And this is going to become, as I mentioned, the super, super important backbone of what makes this RSA encryption actually work. So it seems like kind of a silly little trivial example right now that's kind of a really good practice on doing one of these proofs by cases, kind of the going back to where we just came from. But really what's going on in this thing is actually quite a bit more. This idea that I can jarble up a bunch of random numbers by raising them to powers and kind of looking at this thing in a prime number setting, and it's still going to kick out nice things, becomes a super important tool. This idea that I can scramble things up into a really bad thing, but I do have the ability to unscramble those kinds of things, is exactly what this stuff's all about.